Thanks very much. So apologies for my late arrival, just come straight from Grand Challenges. Look, I'm absolutely delighted to have this opportunity to welcome you all to Stephen's inaugural lecture. And I'm only sorry that I can't be there in person. I know we're in for an absolute treat as Stephan takes us on a journey inspired by his passions for mountains, for glaciers, for landscape change, and the driving effect of climate change. Inaugural gives me a chance to reflect, and I don't know whether it's Stephan's recollection as well, but I think I first met Stephan when I think we were probably both postdocs. I was making a disciplinary transition from archaeology to geography, and I was at a geomorphology conference, and I sat there marveling at Stephan's highly intellectual discussion of geomorphological theory with one of the giants of the field, John Thorns. I think we were sitting outside a pub near Coventry, but I can't quite remember. Stephan might recall. And it made me think about another giant of geomorphological history, Dick Chorley, who reflected that for many geomorphologists, when anyone mentions theory, they instinctively reach for an auger. And that conversation really made me realise that Stephan didn't fit that mould. It gave me a hint of the breadth of Stephan's interests, and if you look over Stephan's publication list, you'll see they range from decoherence, quantum theory, and the implications for for the philosophy of geomorphology, a debate-provoking paper in TIBG, Transactions Institute of British Geography, through periglacial landforms in rock glaciers and alluvial fans in Britain and Ireland. So you can see Stephan's sort of stamping ground in the UK, and then really moving on to the area in which Stephan's really built his international reputation, the mountains and glaciers of Patagonia and the Himalayas. I noticed in the flyer for today's event that it says that Stephan's been fortunate enough to work in many of the world's highest mountain regions, completing expeditions in the South American Andes, Patagonia, Scandinavia, the European Alps and Asia. I'm sure fortune had something to do with it, but I suspect there was an element of planning there. And I'm sure that Stephan's passion for mountaineering has not only drawn him to those landscapes, but also led him to seek to understand their history, how they evolved over multiple timescales, geological timescales, but also the more recent history, how they've responded to climate change, and also how to predict their future. So what are going to be the implications in relation to catastrophic change in terms of fresh water supplies to the societies and communities that depend on them? Stephan's career before coming to Exeter saw him hold roles at Newcastle and Sunderland Polytechnics before they became the universities they are now, at Middlesex, Coventry and Oxford universities, before joining Exeter in 2005. And since joining Exeter, Stephan supported his programme of research that we're going to hear more about, with funding from NERC, from the EU, from learned societies, from charities and from industrial funding. He's innovated in education as well as in research, developing Exeter's first climate-focused MSc in climate change and risk management, and supervised many students in their MScs and 15 doctoral students in their PhDs. Stephan's made a really significant contribution to public debate regarding climate change through both printed and broadcast media, including the prize-winning BBC programme Climate Change, How We're Changing Planet Earth. And he's not been shy of taking that knowledge exchange work into some quite sensitive environments, acting as an expert witness for the Environmental Law Alliance worldwide, looking at the impact of mining on mountain glaciers in the Chilean Andes, especially the Pascua Lama mine, working with the United Nations Development Programme, looking at negotiation documents around the Caribbean island states, and serving as a scientific advisor to Lloyd's insurance market. So to conclude, I know you haven't come here to listen to me, but to listen to Stephan. I hope these snapshots have given you a bit of a glimpse into the multifaceted nature of Stephan's contribution to understanding the science and the social science of climate and environmental change, and why his richly deserved promotion to Professor of Climate and Environmental Change is so timely. So it gives me absolute pleasure to congratulate Stephan on that achievement and to invite him to give his inaugural lecture, Mountain Glaciers and Climate Change, Past, Present and Future. Over to you, Stephan.
Thank you very much. Thank you, Tim. See where we get to. Okay. Right, thank you, Tim. Yes, I do remember that argument I had with John Thorns many years ago, and it was in Coventry. It was outside a pub called Brown's, I seem to remember. But anyway, yes, it was I do remember that. So thank you for that. I'm going to talk to you for 45 minutes or so about mountain glaciers and climate change, past, present, and future. I've got a bad cough and I've got a bit of hay fever. Actually, if it gets any worse, it's going to be a eulogy rather than an inaugural lecture. But so if I do cough, apologies for that. So it really starts. Well, it starts with two things, right? It starts with my father, and it starts with this book. So this book is the Ascent of Everest, 1950, a book about the 1953 expedition. And when I was about 7 years old, I was very ill, a bit not unlike now, and I couldn't go to school. So I started reading through my dad's bookshelves, and I started with The Cruel Sea by Nicholas Montserrat. And then I moved, the second book I read was this one, called The Ascent of Everest. And at that point, I became transfixed. Here was I, a 7-year-old living in the Midlands of England, completely transfixed by glaciers and mountains. And I knew then that I wanted to spend my life working in the mountains. And essentially, my love for mountains and love for mountaineering and glaciers started then. And my father, for very obscure reasons, which I won't go into, my father is a geographer, or was a geographer, and he started. He became my teacher at school and my head of A levels. And he, at the end of each year, he had to write a report for the students. And the first report, when I was in my lower sixth, he wrote, the problem with this boy is his father, and he's, of course, he's entirely right. He did get into quite a lot of trouble with the headmaster, because the headmaster saw this as being a bit flippant. So the next year, when I was in my upper sixth, he wrote that Stephan should not think that he'll go far just by knowing a lot about glaciers, right? And so I'm going to spend the next 45 minutes explaining why I think he was wrong. He's right about most things, but on this occasion, I think he was wrong. So I'm going to talk about the past. I spent a lot of time working. I spent 32 years working in Patagonia, I think 16 expeditions. So I spent a lot of time working in the mountains of Patagonia over the last few decades. So I'm going to talk about past climate change, and then I'm going to go on to the contemporary, what glaciers are doing now and why it matters, and then I'll say something about what the future might hold. So the first thing I want to talk about is Patagonia and the implications of a bipolar seesaw. So here's Patagonia. This is southern South America here, of course. This is all of Patagonia, but the area I'm working in here, I'm working essentially for many years on the North Patagonian ice field. Other ice fields are available in Patagonia, but I worked on the North Patagonian ice field. And we spent essentially many, many years working on the west and on the east of the ice field. I started working on the west initially, but quite quickly I realized it rained too much. So I very sensibly moved to the east, where it's much drier. So we have a very steep climate gradient between the west and the east of the mountains. Now, I need to say something about past climate change. And we need to know this because otherwise the rest of the sort of talk doesn't really fit. So here we have a record of, this is from the Northern Hemisphere. This is by Richard Alley, which is why this is in axis is in degrees Fahrenheit. But here we are the present day. So that's 1,000 years before present. So we're here, we have a cold period called Little Ice Age in the Northern Hemisphere. Climate goes up and down, up and down. Medieval warm periods here, goes up and down, but it's essentially pretty stable over the last 11,000 years of the Holocene. But before that, we have a really rapid, big shifts in climate. We have the Younger Dryas, which is a serious cold event, which affects the Northern Hemisphere. But before that, we have the Voling Alaroth, which is a period of warming. Now, so that's the Northern Hemisphere. So we can see that here. So this is the Greenland record. So we can see the 20,000 years ago is getting, it's cold, temperatures going down and down until we get what's called Heinrich stages. But then it gets warm again, the Voling Alaroth, and then this very cold period called the Younger Dryas. But in Antarctica, it's different. In Antarctica, we don't get warming in the Bolling Alaroth like we have in the Northern Hemisphere. We're cooling, and that's called the Antarctic cold reversal. And during the Younger Dryas event, about 11,700 to 12,900 years ago, we have warming in Antarctica. So essentially then, what goes on in the Northern Hemisphere is completely different from what goes on in the South. When the North is warming, the South is cooling. When the South is warming, the North is cooling. And it's called this bipolar seesaw. And we need to understand that, because one of the questions about Patagonia is, to what we know this Younger Dryas event, this very cold event, occurs in the Northern Hemisphere, but does it occur in the Southern Hemisphere? So Patagonia, because it's stuck right out into the Southern Ocean, and it's the only landmass in the Southern Ocean in the Southern Hemisphere between about 40 degrees and 50 degrees south, is a really important place to understand past climate change and assessing what goes on globally. And we haven't got much data from there. So understanding the timing and scale of glaciations in the Southern Hemisphere helps us fill that gap. And specifically, I looked at three things: the Little Ice Age, which occurred a couple of hundred years ago in the Northern Hemisphere; the last glacial maximum 20-odd thousand years ago, when ice sheets covered much of the Northern Hemisphere and Southern Hemisphere, and periods of time between those, what we call the late glacial. So here's the first thing, is we looked at the Little Ice Age. And the Little Ice Age then is a period of time when glaciers expanded all around the world. And when we first worked in here in Patagonia, that question, we didn't know what the glaciers were doing then. Vanessa Winchester at Oxford and I were essentially amongst the very first people to work on these glaciers. So we worked on a whole range of glaciers on the western side and on the eastern side. And we were essentially either the first or the second group ever to reach these glaciers. So it was pretty pioneering stuff back in those days. Without a whole, mobile phones and satellite imagery didn't really exist, or not to the extent we have now. So we spent a lot of time working in the west. This is a very special glacier, the Sankintin Glacier, for several reasons. One, it's the biggest glacier of the ice field. Secondly, it's the only glacier on the western side where you can actually collect data from. And third, that's where I met my wife. So I spent 6 weeks on this glacier. She was up here somewhere, standing in a bog, I think at the time, trying to camp in a bog. And I walked 16 kilometers down a beach with a bad knee, and I'd had 2 sets of clothing, a dry set and a wet set. And I think she probably smelt me before she saw me. But anyway, I wasn't obviously husband material, as she said later, and has continued to say for the last 25 years. But so that was quite an important place. And what we did is we reconstructed the behavior of this glacier over time, over the last couple of hundred years. So these moraines go back to the 1800s. And we did that for essentially most of the glaciers around the ice field. And that was at the time, pretty pioneering work, I think. And this is the sort of places we get to. So here's the Neff Glacier in 2005. So this is when I did the David Attenborough program, which Tim mentioned. This is where we were camping. And essentially, so these trees are growing where the glacier was in the 19th century. So the glaciers retreated by about 4 kilometers, but also down-wasted. So it's got shorter and thinner. That's the one. Shorter, and so it's retreated from the surface downwards, about 180 meters, and it's retreated. And you can see this so-called trim line all around the ice field. So essentially, these glaciers have all done the same thing. They've all retreated in that period of time. So we then, so Little Ice Age, I normally spend an entire 2-hour lecture on Little Ice Age for my students. So you're lucky you've got away with it in 4 minutes or something. But we then moved on to the last glacial maximum ice sheet in Patagonia, and that's around about 25,000 years ago. And so we did a load of work, and this is with Neil Glasser at Aberystwyth University. So we looked at this ice field. So here's the North Patagonian ice field. Here's the much larger South Patagonian ice field. And here, way out, more than 100 kilometers east of the ice fields, in fact, 150 kilometers, are these huge moraine systems. And this is the longest record of glaciation anywhere in the world. So some of these moraines out here are 1 million years old, right? In the British Isles, we have moraines which are about 25,000 years old, the last glacial maximum, but nothing since then, before then. So this is 1 million-year-old moraines, and there's a good reason why for that, but I haven't got time to talk about it. But Neil, and with Neil, we essentially mapped the entire southern South America, which enabled us then to start putting all the sort of dated assessments of what was going on into context.
And so this is a paper we've just submitted with one of Neil's PhD students, Ingo Wolf. And so we've used, essentially, this is just one of the one of the diagrams from it. This is the LGM, last glacial maximum ice thickness. So it's 3,500 meters to a low of 0. So we can then reconstruct, using remote sensing, reconstruct the thickness and the size. This is an entire reconstruction based on just remote sensing of the whole Patagonian ice sheet, and that matters if we're going to understand future sea level rise and past sea level rise as well. Now, so we know a lot about how far the ice sheet got to, right? We know a lot about its horizontal extent. What we don't know is its thickness. And if you're going to try and understand past climate change, you can't just work on the moraines, because all you do is you get an understanding of the extent of the ice sheet. You need to know how thick it was, because essentially, if your ice sheet was only 500 meters thick, then you could generate a 500-meter thick ice sheet with only a small amount of, say, climate change, increased precipitation, decreased temperature. If, however, it's 2,000 meters thick, then it obviously needs to be either wetter or colder, or colder to generate it. So we need to understand the upper limit. And at the time, the question was, how thick was the ice sheet at different times? And the only record we've got for the whole of Patagonia, in fact, I think the only record we've got for the whole of South America is from Jake Boax's PhD, who's one of my PhD students. So here's Jake sitting on this big plateau surface in Argentina, and you can see these lumps of white granite, and these have come from the ice field. So this is 60 or 70 kilometers from the present day ice field eastwards. And so we're taking rock samples here, and from these high mountains east of the ice field. There's my rucksack. Look at on top of this mountain. These are beautifully preserved erratic boulders being dumped there by the ice sheet. So we need to know the ages of those. And so we produced this paper a few years ago, Jake's paper, and it's the first and only assessment of the 3D structure, I think, of any Pleistocene ice mass in South America. So we can then do this big, long transect, and we can work out, that's the mountains, that's what the mountains look like. They're slightly exaggerated vertically, but we can then work out the upper limits of the ice sheet. And essentially, the whole of Patagonia is open for this work. So we really need to go back and do, great excuse, by the way, to climb those unclimbed mountains. So, this is the sort of work we really need to do to try and understand the ice sheet better. What happened after the last ice age we've got the little ice age just a couple of hundred years ago in the 1700s, 1800s, and then we've got the LGM, last glacial maximum, 25,000 years ago. So what happened in between those huge time periods? And so this is what we're trying to get interested in, is something called the late glacial. Can I get rid of this, by the way? Do you think? Not sure. If I press the wrong thing, no, it's all right. It doesn't have a cross on it. It doesn't matter. But it just means that if I do press the wrong thing, everything goes off, including the lights. So, but here's the late glacial. So here we have there's a North Patagonian ice field, all the mountains around it. And we have this big moraine ridge running out. A moraine is a ridge which has been pushed up by the glacier, made of sediment and rock and stuff, sticking out into this lake. Here we are. This is what it looks like from the air. There's another one from the air. So we needed to date those. So we produced a load of papers over the years. I reproduced over 40-something papers now from Patagonia, but here are just a few of them, looking at the younger Dryas here, early Holocene glacial advances, a whole range of things on the extent of the late Pleistocene Holocene transition. So we're trying to understand what happened during this late glacial period of time. And so what we did is, here's that big moraine again, that big ridge. And there's a colleague of mine, Krista Janssen, sitting on a boulder, which we sampled. There's another boulder which we looked at. Actually, God, that's a terrible photograph. I'm supposed to be taking a sample from a boulder, but it looks like I'm actually depositing one. But apologies for that. I haven't noticed that before. I am actually squatting down. That's what I am doing, squatting down, taking a sample from a boulder, which I'm then going to use to date this glacial advance, because if you can date the boulders, you can then say something about when the glaciers were there. So here then is just one figure from that paper. Here's the North Patagonian ice field, and essentially we've got a whole series of moraines and boulders. Here are the ages here, 9.3, 1,000 years ago, 9.5 thousand years ago. You know, these are then, so we tried to reconstruct what was going on in that ice field at that time. Okay, so that's all I'm going to say about Patagonia. Patagonia is one of the great places in the world to work because there's an enormous amount of stuff which hasn't been done. And if you want to understand global climate change, you have to go to the southern hemisphere. So I'm now going to say something about the present. So what are glaciers? So glaciers are retreating. And I'm going to say something, and we need to know about why they're retreating and what's going to happen. And I'm going to use an idea called paraglaciation. And I'll do exactly what I say to my students. I say, imagine this is a glacier, right? This table, and it's going down this valley, and I'm a valley side. Suspend your disbelief for a second. Call me Cliff. My name's Cliff. Okay. So Cliff is standing here. I've been eroded by this glacier, and I can stand here for as long as I need to, right? I can stand here and talk to you. But if you took this away, I'd suddenly fall down, right? And so essentially what happens, the landscape falls apart. Mountains fall apart once the glaciers disappear. So we call this idea paraglaciation. And I'll just say something briefly about glacial lake outburst floods, which is what I work on a lot, GLOFs, and I'll say something about rock avalanches. Basically, this is in the context of the warming, which here's the warming we can see up to essentially 2020. Here's the warming we see, and the glaciers around the world are in recession because of this warming, right? And it's not just about things like water supplies we need to worry about. It's about what's happening to the valley side slopes, because that matters a lot, and I'll explain why in a minute. So here is the Morterasch Glacier in Switzerland. I climbed that mountain over there in 1982, I think, or 83. This is where the glacier was in 1985. You can see that rock there. That rock is now that rock there. And that's where the glacier was in 2010. It's now retreated even further. And here is in Svalbard. This is what this picture from Svalbard looked like in 1900, 1960, 2015. And when I was there a few years ago, it retreated even further. So we can see all around the world, from the European Alps, the Himalayas, South America, the Arctic, we can show that glaciers are in recession. And what happens, now that's not helping, right, go away. No, it's not going to go, is it? I'm not going to. Oh, hey. Glacial recession produces these things called glacial lake outburst floods, right? So here's a typical example. This is in Patagonia. Vanessa Winchester and I walked past this valley back in about 1999 or 2000. And we came up through here, this valley, and I took this photo to where I'm taking a photograph, and it was completely covered with trees. And about 2 years after that, the moraine which I'm standing on here failed. And that is an 18-meter high boulder there, and that's me in yellow trousers. Had I been there when it happened, I suspect my trousers might have been a different color, but that's a large boulder, and with big boulders on top of it. So these are the size of footballs. And essentially, when you've got 18-meter high wave traveling down that valley, produces this enormous glacial lake outburst flood. Now, that didn't kill anybody, thankfully, but in places like Peru in 1947, I think 4,000 people were wiped out in a city. So in the city of Juarez. So these in many parts of the world are extremely damaging. Here's a right. There we go. Here's another picture taken from Annacona's paper. So there is the glacier. There's a moraine there, and essentially this big wave of sediment and water has come down here. Impact wave has cut through the vegetation, produced big boulders. Now, the trigger for that was a large rockfall associated with this idea of paraglaciation. It fell into the lake, huge lump of rock, fell into the lake, glacial lake. Glacial lake produces what's called a Seiche wave, which then rips out the moraine. Then the moraine just made of massive boulders, the size of this room, down valley, downstream into the main valley. So you can see the size of some of these boulders around here. So that's where the rock avalanche, we call a rock avalanche, came down into a lake and created that moraine dam, that impact. So these things happen all over the world in high mountains. So this is a famous mountain in Himalayas called Ama Dablam, and that glacial lake outburst flood there's a big lake in here, and came in through here, through this moraine, ripped out this moraine, and you can see where this is the 1970s this happened, I think, and then very nearly wiped out this quite large village here. This is on the walk up to Everest Base Camp. And here's another one. This is where I was in September last year in the Peruvian Andes. Again, there's a big glacial lake outburst flood came through here, ripped out, took out this entire moraine here and left behind this big channel. So these occur all over the world. And the question is, okay, how many are there and what's their relationship to climate change? Because everybody says these are caused by climate change. Climate change will make these things worse and they're getting more frequent and bigger over time. So I, in 2010, decided to work out whether that's true or not. So I produced the first, and with colleagues, produced the first global inventory of glacial lake outburst floods. So we can show that all mountain regions, this is the European Alps, this is the Canadian Rockies, Pamir and Tiantian, Hindu Kush Himalaya, and the tropical Andes. And using 3 different data sets, we could show that all of these regions are undergoing warming, right? And we should then, if they're undergoing warming, the glaciers should be retreating and then the gloss should be getting more frequent. And they're not, right? So the gloss peak globally is in the 1960s. And since the 1960s, the number of gloss has gone down. Now, there are lots of reasons why that could occur, and I haven't got time to talk about them, but it shows the relationship between what happens in the mountains and what the driver is climate change, is really complicated. So we need to understand how these complications occur. Other hazards, well, this is one which occurred, we published this in Science a couple of years ago. In 2020, an enormous lump of rock fell off this 6,000 meter peak. Now, this lump of rock is about, the surface area is about the size of the campus, right? And it's not only that, it's 180 meters thick, right? So it's a big lump of rock, fell off, fell 3,000 meters, hit a glacier, melted the glacier almost instantaneously because of the frictional heat. And that produced an enormous wave of rock and debris, which came down into this valley and traveled up 600 feet up the other side of the valley. So if you'd been on the other side of the valley, hundreds of feet above the valley floor, and were taking photographs, you would have been killed by it. And this was an enormous feature, and sadly killed over 200 people. And the question is, was that caused by climate change? When this happened, The Guardian and other newspapers said, oh, this is caused by climate change. We think this is really, really difficult to say. So we've got the relationship between climate change and these sorts of massive events is really difficult. Here's another enormous rockfall. This rock, that is 6 miles long, that rockfall, right? So there's a rock avalanche come off this big mountain here in Alaska, Glacier Bay, and produce enormous amounts of debris onto the glacier surface. So the question is that caused by climate change? Will climate change make those worse? We don't know the answers, but those are some of the things we need to understand. That's all I'm going to say about the present in terms of what I do. I want to now the sort of third area of my research is about the future. What's going to happen about the future? Well, we know that climate change is going to continue. All the representative concentration pathways and SSPs, basically how much carbon dioxide we put in the atmosphere, produces warming. Essentially, if we're on an 8.5 watts per square meter pathway, we're going to end up with lots of warming. And if we're a bit lower than that, we won't. But we're not going to keep to 1.5 degrees Celsius. That essentially is not possible, given what we know about climate sensitivity. This is what the world looks like. This is where we are. We're just at about 1 degree Celsius warming now. And the Arctic is one of the places which warms up the most. But other parts of at the moment, right? So this is where we are now. But but in the parts of the oceans don't warm up at all, right? Now, when we get to what we might get to, say, at 4 degrees Celsius by the end of the century, then the Arctic actually warms up to at least 7 degrees, perhaps more. But there's quite a lot of variability. The land masses warm up more than anywhere else, and the oceans don't warm up as much. So we need to understand climate change if we're going to understand what's going to happen. So newspapers then have said, look, actually climate change is going to radically affect the Himalayas, right? The Himalayas, the high mountain Asia, the glaciers of high mountain Asia provide the water which regulates the water for 40%, nearly half of all the world's population, 40%, right? So that's a lot. And so we need to understand what Himalayan glaciers and high mountain Asian glaciers are doing. So there's a lot of understandable policy interest, but also, excuse me, policy interest, but also scientific interest in what's going to happen to these high mountains. Right, so this mean for glaciers? Okay, so we can model glaciers using climate modeling, global climate models, and this is a project which I was part of a few years ago. We use the Helix project, which is funded by the European Union, run by Exeter and Met Office, high-end climate change in extremes, using global climate models, right? These are numerical, mathematical models. We use a model called HADGEM, Hadley Centre, which is in Exeter, the Met Office. GEM stands for Global Environment Model. So HADGEM 3, we ran it for a big radiative forcing driver, and then we tried to look at what this means in terms of temperature change and snowfall relative to the present day for all of the world's mountain glaciers, all of the world's glaciers, essentially, apart from Antarctica and Greenland. So all the world's mountain glaciers. And we can show, this is the area we're interested in, we can show that essentially everywhere, snowfall reduces and temperature rises, right? We sort of knew that. So why do we have to spend millions of pounds on models? But hey, you know, I should be careful. I don't know who's listening. What we have got, of course, a whole series of other models we can use. So there's a French model there, American one there. So we can use these models to assess when we might reach these specific, what's called specific warming levels. And so essentially what it shows is that glaciers reduce in mass, right? Because of climate change, they're going to get smaller. Well, essentially, yeah, we knew that, but now this is a 2019 paper, we were able to put real numbers to this. And essentially, when you get to 4 degrees Celsius warming, we think that, well, this model argues that glaciers will reduce in mass by over 90%. So in other words, suddenly you've got billions of people in India and Pakistan and all the stands, Kazakhstan, Uzbekistan, Turkmenistan, all these others, and China and Tibet. Millions of people, and all the glaciers are going to melt. So this is a really big issue. So the question we have to ask is, that's what the climate models say, but the question is, will all glaciers melt? And I think, no, they'll undergo a transition, they will change. So that's me standing on an enormous lateral moraine this is the Khumbu Glacier. Everest is up in the clouds up there. So this is a big glacier with lots and lots and lots of, look how dark it is. There's no ice there, you can't see the ice. When you're walking across that glacier, you walk for literally hours without seeing ice. So essentially we need to understand the debris, the rock debris. We've seen big lumps of rock falling onto glacier surfaces. We need to understand that because of the impact that has on glacier mass balance. In other words, how quickly they melt. So here's a glacier which I was working on just around the corner there last May. So here's that's Tawichi, I think. This is Everest is way off to the left. Here's a glacier called Nzumpa Glacier. Again, a big lateral moraine ridge there. But look how flat it is. It's flat for kilometers. And it's covered with lakes, which are very unstable. But it's covered with debris. You hardly see any ice. So debris cover, rock material and other stuff, it falls onto the glaciers, plays a major role in protecting those glaciers from warming, from climate change. So we need to understand the role of glaciers, rock glaciers, and ice-cooled moraines, because debris cover is really important. It really changes the way we look at glaciers. So here's an example from Central Andes in Chile, which I took a few years ago. And essentially then, if you're looking from space, if you're looking at from aerial or satellite imagery, you'd say, where are the glaciers? You go, well, there's a bit there, there's a bit here and there and there. Actually, ice covers or is underlaying the whole area. So this is all underlain by ice. That lateral moraine is all underlain by ice. Where I'm standing is probably underlain by lumps of ice. So there's ice everywhere, much more ice in the system than we ever imagined just by looking at satellite images. So we need to understand what that debris cover does. I don't really need to show that. It just shows that essentially debris cover slows down the rate of melting. So a debris-free glacier melts very quickly. A debris-covered glacier melts hardly at all. Just a few centimeters. It takes a few centimeters of debris on a glacier to stop it melting. And since most glaciers in the Andes, and most glaciers, well, many of them in the Himalayas, do have debris because these valley-side slopes are failing and falling down, that makes a big difference to how they behave. So we need to understand what glaciers do and how they turn into debris-covered glaciers. But then there's another transition, and that's how they turn into rock glaciers. So these are rock glaciers here in the Himalayas. It's a bit like if you had a big pail of porridge, right? And you poured it slowly. It would make beautiful ridges, compression and extension flow ridges. And it flows very, very slowly. It's a mixture of rock and ice. And it flows like a viscous, what we call viscous flow. It's a bit like porridge, flowing off these mountainsides. They're remarkable things. I won't go into that, but basically these are some definitions of rock glaciers. Essentially, you've got quite a lot of ice in these things, and we'll find out how much ice in a minute. So I suddenly realized, of course, that, well, that actually we shouldn't just be looking at the climate models to understand what water supplies are going to do. We need to understand the rock glaciers. How many are there? Where are they? How much ice is in them? We don't know. So here's some lovely rock glaciers in Alaska. Look, if you looked at this from a satellite image, you'd say there's no ice there at all. No glacier there at all. But this whole area, which is hundreds of meters wide and probably a kilometer long, is underlain by ice. There's ice throughout the system. So we really need to know about what these things are doing in the Himalayas to find out. So we produced, Darren Jones, one of my PhD students, we produced the first rock glacier, global rock glacier inventory a few years ago. And we estimated there was something like, well, up to 50 billion cubic meters of ice in these, right? And of course, many of the ice classes will transition to form these things. We then applied that to Nepal. We did the first assessment for Nepal, again with Darren. And clearly there are lots of them, over 6,000 rock glaciers. We then applied that to the whole of the Himalayas. And there are about 25,000 rock glaciers in the whole of the Himalayas. And that paper came out 2021, I think. And here's nice pictures of rock glaciers here. Here's one which is rather probably relict. In other words, it's probably not much doing very much. It's not active. Here's a much more active rock glacier here. These are both in the Manaslu region of the Himalayas, just west of western Nepal. 25,000 of them. And we've just about to produce the first Tibetan, for the whole of the Tibetan plateau. And that's over 31,000 rock glaciers. And we've used, essentially, for the first time, artificial intelligence. Right, so I can identify what a rock glacier looks like. Let's get some photo. So I can identify that's a rock glacier. In fact, there's lots of them. There's a rock glacier there and all over the place. It'd be really nice to get a computer to do that, because if you've got 25,000 of them, that takes quite a long time. So we're using artificial intelligence and training it to assess the difference between rock glaciers and permafrost extent for the whole of Tibet. And so that paper will be coming out, will be submitted, I should say, by the end of, probably by next month, I should think. Now, what we haven't got is any understanding of how much ice is in them. We can estimate it, right? But there are 25,000 of them in the Himalayas. They're all at 5,000 meters. I'm not getting any younger. I can't possibly go around at 25,000 rock glaciers and work out how much ice is in them. So we need to use other techniques. And so what we've done is used, in fact, May last year, we were working at 5,000 meters, which is 16,000 feet for those of you of an imperial requirement. First observational assessment of ice content. And this is GPR on a Gokyo rock glacier. So this is the rock glacier. It's a huge thing. And this is the part of the GPR we were using. Essentially, you have to put a massive rucksack on your back and pull this thing over this rock glacier at 16,000 feet. Which is probably where I got my cough. And so here's the transects. We did 3 kilometers worth of transects across this rock glacier. There's the Nzumpa glacier, which I showed to you earlier. And here's my rock glacier just there, almost joining it. So we did all these transects across here. It was an amazing trip. So my kit was carried up by helicopter and dumped at Gokyo, 16,000 feet, 5,000 meters. And then I and a guy called Matt Peacey and others, a couple of others, walked up there, spent a week getting up there because we had to acclimatize. So we get there, do all the work, and then this guy comes in, and his name is Aldo Moro, and he's one of the world's top mountaineers. He flies in his helicopter. He's also the guy who's done the highest ever rescue in a helicopter, about 7,000 meters on Everest. Flies in at very high speed, stops his helicopter. We jump on, no seats because they've got too much kit. So we've got no seats. So we're sitting there, and he goes flying off down this valley. And he's one of the world's top mountaineers. So my wife said, "Did you talk to him about mountaineering?" And I said, "No, he was too busy not crashing into 6,000 meter peaks as we're going down this valley." And it took about 15 minutes to get down. It took us 7 days to get up there and 15 minutes to get down, which is I'm now converted to to that mode of travel. So anyway, so this is where we did, and we then produced a GPR survey, and we haven't finished this, haven't finished the processing, but we assume that we're making the assumption that there is large bodies of ice in there. So that is essentially what, that's about 50 meters deep and about 200 and something meters long. That's just over, that's only, so we haven't done all of this bit. There's loads of stuff we haven't done, but these are the bits we have done. And we can demonstrate, well, we suggest that this is water, ice within this rock glacier. And that is equivalent to, I put this in just because that probably doesn't mean very much, but that may well do. There's quite a lot of ice in this rock glacier. And that's only one out of maybe 50,000 or so of these in the Himalayas. And this is the highest ever GPR survey, I think, done on rock glaciers anywhere in the world. So, and it's the only one in the Himalayas. And we can't extrapolate from 1 to 25,000, but it would be nice to be able to do that. Lots of other research questions. We don't know. We know that rock glaciers contain at least 20% water. We've actually just produced a paper which was published yesterday in the cryosphere, and we think actually the ones we looked at is probably up to 70% of water, but we don't really know. They're likely much more resilient to climate change than glaciers. We really don't know really how many there are. We've made some estimates. We don't know how many. We don't really know how much ice is in them. We can make guesstimates. We don't know the response to climate change or how quickly they're going to respond, nor do we know which glaciers undergo that transition. They've got loads of glaciers in the Himalayas. Is that one going to transition to a rock glacier, or is this one? Which ones do it and why? What are the controls on it? Modeling these is really difficult. We don't know if the water supplies can be accessed, but this is really important for UN Sustainable Development Goals. I think it's number 13 about fresh water. Giving fresh water to these high mountain communities. We need to know these questions. So to summarize then, so I've done three things. Well, I've done, my three things in this talk are understanding past climate change, mainly in Patagonia, but also elsewhere, lots in the Himalayas, but also in Peru and in Britain and other places. So we need to understand past climate change. We need to understand it gives us an idea about how glacier responses, how they responded to climate change in the past, gives us insight into how they might do that in the future, right? We need to understand the past, or understand the future. The past gives us some insight. We also need to know how Earth's surface systems work, and that helps us understand climate change impacts. Everyone talks about impacts. Well, impacts are about as much about geomorphology as almost anything. We need to understand geomorphology if we're going to understand impacts. And we can't adapt to climate change if we don't know what the impacts are, right? So this is part of this big debate. So I want to end by saying thank you to all my colleagues who've made all of this possible. This is just some of them. So thank you. Sorry, it's my wrong lecture. This is. I want to say thank you to my colleagues. This is only a fraction, but these are some of the people I've worked with and published with. I'm not going to go through all of these. Just a couple of these people are sadly no longer with us. So Dave Keane at Coventry University, Professor Dave Keane, a great colleague of mine and quaternion scientist, and Doreen Massey at Open University, who died a few years ago, world famous human geographer. So I would say thank you. I'm not going to list them all, but thank you very much. But the people I really want to say thank you to are these people. Dave Passmore, one of my best friends, who I worked with, started working with on archaeology in 1987. It shows how old I am. He's a world expert archaeologist at the University of Toronto. One of his particular strengths is standing in holes, and he's doing that beautifully there. So we work a lot in Europe. Neil Glasser, who I think I've done about 10 expeditions to Patagonia with him. I've been working with him since 1991. So that's Neil standing in front of, and we've worked in Peru and the Himalayas a lot. That's him standing in front of Manaslu, the eighth highest mountain in the world, when we were there a few years ago. Olaf Bundrich, who's a good friend of mine. He's done a lot of supporting my research in Patagonia and helping me go mountaineering, and we climbed a lot. So I shouldn't say that because I'm supposed to be working, but I was working. We're just about to make the first winter ascent of the mountain up there for a few days. So there's Olaf. Jasper Knight at the University of Witwatersrand in South Africa, who I've done a lot of work on sort of theoretical geomorphology. He's a great guy. He sadly doesn't know how to put a rucksack on, but he's one of the top geomorphologists who I work with. And Karen Anderson of this parish. And we were working, been working all over the place, but Himalayas, but also on Ben Nevis, looking at little ice age glaciers. There's a picture of Karen, who's in the early stages of hypothermia, because we were up there one May and it poured with rain and just horrible. But anyway, so I want to say thank you to these people because as well as everybody else, because these without the support of my colleagues, this would have never have happened. But most of all, I want to say thank you to my family. My family, William here, Floss, and Lily. Lily's not here, sadly, but she's traveling in Europe. But these are clearly grown up now. I can't say that my wife has, and Tessa. And essentially, none of this really. I mean, they've been amazingly supportive over the years, and allowing me to go to these places and work in these places. So I dedicate this talk to them. So thank you for listening. What happens now?
So I think, Stephan, can you hear me, Stephan? Down
yes.
here.
Hi, Dan.
If you unshare your screen, I can
Right.
do the final formal
I need
bit.
help here. How does this work?
Good question. Anyone know? Back onto Teams.
There's Tim.
There we go.
Stop sharing.
There we are.
There we go.
Can you hear me okay?
Yeah. Thanks, Dan. Yeah, I think you're there.
Great. Okay. Well, it falls to me to do the final part of this. This is always so much easier if I could be in the room with you. So apologies for that last minute change of plan and not being able to come down to Penryn. But yeah, I mean, this is my task is to do a very short vote of thanks. And there's one thing I've learned in doing votes of thanks for things, when there are drinks and things waiting outside. One, to keep it very short. Two, to make sure I thank the main people. And the main person to thank is obviously Stephan for an absolutely fabulous and perfectly pitched lecture, may I say. Also, Stephan, just the right level. I think inaugural lectures are very difficult to get right, and you did it absolutely spot on. So thank you very much for a fascinating lecture. And as Tim said, it really is just one bit of your work. I know it's been a main part of your work, but I also look back at your publications, and it's quite incredible the range of things you've been involved in over the years. So I won't repeat the kind of that sentiment too much, but I was particularly fascinated by the geomorphological work in relation to conflict and war in the past, and obviously the work with archaeologists in terms of different interpretations of the same landscape from an archaeological and geomorphological point of view. So you are very much a polymath of the geomorphological world, and you showed that tonight in your very excellent lecture. So really, just two things to say in terms of thank yous is, besides thank you very much, Stephan, for your lectures, also to thank all the local organisers. I know it takes a lot of effort to put these things together, so particular thanks to Ellie and also to Jen, and also echoing the support that all of those people have given you over the years, and particularly fascinating story there about your father, and to thank your father, I suppose, for putting that book into your hands in the first place. I guess if you'd taken up the message in the Cruel Sea, then perhaps you would have been doing something completely different instead. But just shows how these pivots work in our lives. But yeah, brilliant exposition of the subject area and a fantastic inaugural lecture. So thank you, Stephan. Thank you to everybody, and please go and enjoy your drinks and nibbles afterwards. Round of applause, I think.
Thank you very much.